predicting the relative length and energy of chemical bonds. Okay, so you can only compare apples with apples for this, okay? So in this particular question, we're comparing carbon-carbon bonds by the look of it, okay? So what's the difference between a single bond, a double bond, and a triple bond? Well, the number of electrons, right? So a single bond has only got 2 electrons, okay? And remember where those 2 electrons are. They are generally situated in between 2 nuclei coming together. So you can imagine you've got like a positively charged nucleus from one carbon and a positively charged nucleus from the other carbon. I guess I can put them in little circles to show that that's a carbon atom, right? And then somewhere in between them, you have like fuzzy, wuzzy places where electrons could be, right? Because that's what quantum tells us, right? So I'm just going to use, that's an electron. That's an electron, right? They're somewhere in between those 2 nuclei, okay? So you're going to get a certain amount of repulsion between those nuclei, depending on how much of the positive charge those 2 electrons in the bond have, right? So if we have a double bond, well, a double bond, if I can actually draw anything, a double bond like that is 4 electrons being shared, right? So then if we go back to our little model here, I've got more electrons. Again, I don't know exactly where they are, but they're somewhere in that fuzzy wuzzy space in between the nuclei. So if there's more negative charge in between those 2 nuclei, those 2 nuclei are able to get closer together. So that means the bond gets shorter, okay? And it's also going to be stronger because think about like electrostatics, like the higher magnitude of positive and negative charge you have, like the more attractive forces you're going to have. So then if we have a triple bond, which I guess I'm going to have to draw instead of being lazy and using like the equal sign, how many electrons is in a triple bond? 6 electrons, okay? So if we have 6 electrons in between those 2 nuclei, then you've got even more negative charge mitigating the repulsion between those 2 positively charged nuclei. Therefore, the nuclei are going to be able to get closer together. Your bond length is going to be shorter, and there's going to be more energy associated with that bond. So it's going to cost you more to break, okay? So triple bonds, the shortest and the strongest, and the single bonds are the longest and weakest, okay? And obviously double bonds are somewhere in between. So now looking at our option here, our single bond is going to have the longest length. I'm going to take 1 as being the longest. I'm not sure exactly how Alex describes it, right? And it will have the weakest energy. So it'll cost the least to break. Then the double bond's going to be in the middle. So it'll be, if I can make this typey thing work, so it'll be in the middle of the length. And it will also be the middle energy, whatever those number options are. And then the triple bond will be the shortest length, but it'll be the highest energy. All right, so I hope that is helpful for you guys. Make this thing stop.